Understanding the global interpreter lock GIL in Python. What is the global interpreter lock GIL? The global interpreter lock, commonly referred to as GIL, is a mutex that protects access to Python objects, preventing multiple threads from executing Python bytecode at once. This means that even if you have multiple threads, only one thread can execute Python code at a time. The GIL is particularly relevant in Python's Python implementation, which is the most widely used version of Python. Why does GIL exist? Memory management. Python uses reference counting for memory management. The GIL ensures that only one thread manipulates reference counts at a time, which prevents memory corruption. Simplicity. The GIL simplifies the implementation of Python's memory management and makes it easier to integrate with extensions. Implications of the GIL. 1. Multi-threading limitations in CU-bound applications. The GIL can be a bottleneck because only one thread can execute Python code at a time. This means that multi-threading may not lead to performance improvements for CU-bound tasks. I/O-bound tasks. For I/O-bound tasks like network requests or file I/O, the GIL is less of an issue, as threads can release the GIL while waiting for I/O operations to complete. Example of the GIL in action. Let's explore a simple example to demonstrate the impact of the GIL on multi-threading in Python. Example code: Python import threading import time function to simulate a CU-bound task. Def CU-bound task. Printf starting task and count 0 for I in range 10 7 count I. Printf task and completed with count create and start multiple threads for I in range 4 creating 4 threads thread threading. Thread target CU-bound task args I threads append thread start wait for all threads to complete for thread and thread join print all tasks completed. Explanation of the code. 1. CU-bound task function. This function simulates a CU-bound task by performing a large number of additions in a loop. Each thread will execute this function. Creating threads. We create 4 threads, each executing the CU-bound task function. Starting threads. The threads are started almost simultaneously. Joining threads. We wait for all threads to complete before printing the final message. Observations. 1. Performance. You might notice that even though we created 4 threads, the performance may not be significantly better than running a single thread for CU-bound tasks. This is due to the GIL restricting execution to one thread at a time for Python bytecode. Timing. If you want to measure the timing, you could add timing logic around the thread execution to see how long it takes with multiple threads versus a single thread. Comparison with multiprocessing. If you want to take full advantage of multiple CU cores in Python, you can use the multiprocessing module, which spawns separate processes each with its own Python interpreter and memory space instead of threads. Each process has its own GIL. Here's how you can modify the example using multiprocessing Python. From multiprocessing, import process def CU-bound task in printf starting task and count 0 for I in range 10 7 count I. Printf task and processes plus create plus plus for all purposes pro while in this version, each process runs in its own Python interpreter, allowing true parallelism by bypassing the GIL. This makes it suitable for queue-bound tasks. Conclusion: the global interpreter lock is a key feature of Python's Python implementation that simplifies memory management but can limit performance in multi-threaded queue-bound applications. Understanding the GIL allows developers to make informed decisions about using threading versus multiprocessing based on their specific use cases. For queue-bound tasks, prefer the multiprocessing module, while for IO-bound tasks, threading is often sufficient.